When most people imagine the universe, their minds drift to luminous spirals of galaxies, blazing stars, and glowing nebulae. Yet, between these islands of light stretches a darkness that seems absolute. These regions are called intergalactic voids, vast expanses spanning hundreds of millions of light years, apparently empty of stars, planets, or any trace of familiar matter. For much of the 20th century, astronomers assumed these voids were simply what they appeared to be: a cosmic desert, a vacuum where nothing resided. The term void itself carried a philosophical undertone, an echo of the ancient fear of the keinon, the Greek notion of the terrifying nothingness outside the material world. But modern cosmology has forced us to abandon the comfort of this illusion. The empty spaces are not empty. Instruments capable of probing across multiple wavelengths, radio, X-ray, ultraviolet, have begun to reveal faint, hidden signals. They tell us that the darkness is not a void in the truest sense, but rather a veil concealing diffuse structures. This discovery has reshaped our understanding of the cosmos, suggesting that what lies between galaxies may be just as important as the galaxies themselves. The first cracks in the assumption of emptiness appeared in the mid-20th century, when radio astronomy was still in its infancy. Observations hinted that radio waves traveling across cosmic distances were being subtly altered, delayed, or scattered. These distortions could not be explained by interstellar dust alone. They implied a medium, sparse but real, permeating the apparent void. Later, the advent of powerful space-based telescopes like the Chandra X-ray Observatory and the Hubble Space Telescope deepened this suspicion. Against expectations, they detected thin threads of hot gas and plasma stretching invisibly between galaxies, faint but undeniably present. These revelations produced a paradox. If the intergalactic voids are filled with hidden matter, why do they appear so perfectly black? The answer lies in density. On Earth, a cubic centimeter of air contains around 10 billion trillion molecules. In contrast, the intergalactic medium might hold only 1 atom per cubic meter, far too tenuous to glow with visible light, yet enough to distort high-energy photons over billions of years. The void, then, is not a pure absence, but a near vacuum haunted by traces of material so dilute that our senses fail to register it. This subtle presence resonates with the way the human brain perceives silence. Neuroscience tells us that absolute silence is unbearable for the auditory system. In an anechoic chamber, an environment where all echoes and external sounds are eliminated, subjects often report hearing phantom noises, such as their own heartbeat, blood flow, or imagined hums. The brain, confronted with nothing, manufactures presence. In much the same way, when astronomers gazed into intergalactic space, the instruments eventually revealed that nothingness itself was a kind of illusion, hiding structures too faint for our primitive eyes. The illusion of emptiness carries profound implications. Human cognition is biased toward objects, edges, and boundaries. Gestalt psychology has long documented our tendency to perceive discrete shapes against backgrounds, to separate figure from ground. But the cosmic void undermines this duality. Here, the ground itself becomes the figure. The darkness we dismissed as background emerges as a dynamic participant in the cosmic story. The intergalactic spaces, once ignored, now appear to shape the behavior of galaxies, influencing their movements and evolution in ways we are only beginning to discern. Ancient traditions, too, hinted at this paradox. Taoist philosophy described the universe not as a collection of solid things, but as a balance between the 10,000 things and the void that holds them. The Tao Te Ching speaks of the usefulness of emptiness, the hollow in a vessel that makes it capable of holding water, the absence in a room that allows for habitation. What appears as absence is, in truth, a subtle presence. Modern cosmology, though built on mathematics and measurement, seems to be rediscovering this truth on the grandest scale imaginable. Yet this reframing of the void also awakens unease. If what appears empty is in fact populated by hidden matter, what else might be concealed within the vast blackness? Here, cognitive psychology offers another layer of insight. The human fear of the dark is not only a fear of absence, but of hidden presence, an evolutionary bias to suspect that something unseen may be watching. Experiments on sensory deprivation show how quickly the mind begins to project forms and patterns into darkness. In a similar way, our cosmic instruments are now uncovering faint signatures where we once assumed there was nothing, forcing us to confront the possibility that the darkness between galaxies may not be passive but structured, active, and perhaps decisive for the fate of the universe. Every new wavelength we open, infrared, ultraviolet, X-ray, seems to whisper the same unsettling message. The void resists emptiness. Its thin plasma, invisible scaffolding, and faint distortions in light suggest an architecture we cannot yet fully map. And as the resolution of our tools increases, the illusion of nothingness continues to dissolve, replaced by something stranger. A silence that is not silent. A darkness that conceals more than it reveals. A hidden stage on which the largest forces of the cosmos quietly perform. The faint structures hidden in the intergalactic darkness raise a deeper question. Why does the universe behave as if it contains far more matter than we can observe? The galaxies themselves betray the mystery. When astronomers first measured the rotation of spiral galaxies in the 1970s, they expected to find that stars at the edges moved more slowly than those near the center, just as planets farther from the Sun orbit at slower speeds. Newtonian mechanics dictated that the visible mass, the stars, gas, and dust we could account for, should determine the gravitational pull. Yet Vera Rubin and Kent Ford's precise spectrographic observations revealed something inexplicable. The outer stars were not slowing down. They orbited at nearly the same velocity as those closer to the galactic core. This phenomenon, known as the flat rotation curve, implied that galaxies are surrounded by vast halos of unseen matter. The discrepancy was not small. In some galaxies, the visible matter accounted for only a fraction of what was required to explain the observed speeds. The hidden component seemed to outweigh luminous matter by a factor of 5 or more. The implication was unavoidable. An enormous reservoir of invisible mass dominated the structure of the cosmos. What came to be known as dark matter became one of the most enduring enigmas of modern physics. It was not merely an abstract correction for equations, but a tangible gravitational presence, exerting real force while remaining imperceptible to telescopes. The unsettling implication is that the galaxies themselves are like shadows of something larger, luminous ornaments pinned upon an invisible skeleton. Cosmological surveys using gravitational lensing, where light from distant galaxies is distorted by the gravity of intervening mass, have repeatedly confirmed that much of this unseen material does not reside within galaxies at all, but may extend through intergalactic space in vast halos and filaments. The problem of missing mass, then, is not confined to galactic interiors. It pervades the universe on scales so large that the luminous cosmos may represent little more than a residue of something else. In psychological terms, the missing mass resonates with the way the mind constructs perception. The brain does not passively receive the world. It fills in gaps with inferences, predictions, and unconscious biases. Cognitive neuroscience has shown that up to 90% of the sensory information reaching the cortex is shaped not by the raw input from the senses, but by feedback loops from higher-order areas, imposing expectations upon perception. Just as dark matter shapes the visible universe without being seen, unconscious neural processes shape our conscious world without ever revealing themselves. Both serve as invisible scaffolds, defining structure while remaining outside direct awareness. This analogy underscores why the missing mass feels more disturbing than a mere scientific puzzle. It hints that reality may be guided by hidden determinants, forces that we can measure only by their distortions upon the things we notice. The psychological discomfort here mirrors the unease of Freud's concept of the unconscious, something both intimately present and inaccessible, exerting influence while refusing disclosure. For cosmologists, the void between galaxies may function as a kind of unconscious of the universe, the unseen foundation upon which visible forms depend. As detection techniques advanced, other anomalies reinforced the necessity of hidden mass. Clusters of galaxies, for instance, move with velocities far too high to be explained by the gravity of their visible contents. X-ray observations reveal immense clouds of hot gas that should disperse into space, unless held together by far greater gravitational fields than luminous matter can provide. The famous bullet cluster collision, observed in 2006, offered perhaps the clearest illustration. Two clusters had collided, separating their visible gas from the bulk of their mass. Gravitational lensing maps showed that the true gravitational cores had passed through one another largely unaffected, composed of matter that neither emitted nor absorbed light. Yet this knowledge brings little comfort, for the identity of this matter remains elusive. Despite decades of experiments, sensitive underground detectors shielded from cosmic rays, high-energy particle accelerators probing for exotic particles, satellite missions searching for faint annihilation signatures, no direct evidence of dark matter particles has been obtained. The universe insists upon their presence, yet it withholds their form. Such absence of resolution leaves us suspended between recognition and ignorance. Just as perceptual illusions exploit the brain's need to impose order upon ambiguous stimuli, dark matter exploits our reliance on light to define reality. We are accustomed to believing that what we see is what exists, yet the cosmos appears structured by what cannot be seen, suggesting that our instruments, like our senses, are tuned to a narrow range, blind to the majority of what sustains the world. The consequence of this realization is not simply academic. It shifts the center of gravity in our understanding of existence itself. If galaxies rotate under the sway of invisible halos, and if clusters of galaxies are bound together by unseen hands, then the luminous stars and planets we revere may be little more than epiphenomena, surface details riding upon hidden currents. And if so much mass is missing from view, it becomes natural to wonder whether the very darkness between galaxies, the very regions once dismissed as void, may conceal the key to forces shaping the future of the universe itself. The effort to understand the missing mass inevitably led to new ways of mapping what cannot be seen. Light, though central to human perception, became inadequate as a tool. Astronomers turned instead to the distortions and echoes that light undergoes when it passes through the hidden structures of the cosmos. In doing so, they began to reveal a vast framework underlying the universe, a framework invisible to the eye, but undeniable in its gravitational influence. One of the most powerful methods emerged from Einstein's general theory of relativity: gravitational lensing. According to relativity, massive objects curve the fabric of space-time, bending the path of light traveling through it. A distant galaxy viewed through an intervening cluster of mass may appear stretched, smeared, or multiplied into arcs and rings. These distortions act as signatures of invisible matter, betraying the presence of something that deflects light without shining itself. Weak lensing, a more subtle version of this effect, allows astronomers to map the distribution of unseen mass across enormous swathes of sky, revealing a cosmic architecture that luminous matter merely traces. The resulting maps have overturned the picture of a random universe. Instead of scattered islands of galaxies, they reveal a cosmic web, a vast lattice of filaments and nodes connecting clusters across hundreds of millions of light-years. The galaxies we see are not arranged haphazardly, but cling to this hidden scaffold, like dew droplets suspended on the threads of an invisible spider's web. Simulations of large-scale structure formation, such as those produced by the Millennium Simulation Project, show how tiny fluctuations in the early universe amplified under gravity to form this intricate network. The luminous galaxies are only the brightest knots. Most of the substance lies within the dark filaments stretching between them. The eeriness of this revelation lies not only in the scale, but in its resemblance to the neural patterns of the human brain. Studies comparing the topology of the cosmic web with that of neural networks have found striking similarities. Both systems are organized according to principles of efficiency, clustering, and connectivity, despite differing by more than 20 orders of magnitude in scale. This is not a claim of direct equivalence, but the parallel unsettles the human imagination. The largest structures of the cosmos mirror, in their geometry, the hidden architecture of thought. In psychology, such patterns touch upon the human propensity for pareidolia, the tendency to see structure where none is consciously designed. But in the case of the cosmic web, the structure is real, mathematically demonstrable, and physically consequential. The illusion, if any, lies in assuming that matter defines form. Instead, it appears that form emerges from forces unseen, with visible galaxies only inhabiting the scaffolding built by an invisible substrate. The human brain, trained to privilege objects, struggles to comprehend a universe where the true determinant is not the things, but the hidden framework between them. Beyond lensing, other techniques reinforce this vision. Observations of the cosmic microwave background, the faint afterglow of the Big Bang, show minute fluctuations imprinted by the distribution of matter in the early universe. These anisotropies, mapped with exquisite precision by missions such as WMAP and Planck, correspond to seeds of structure that grew under gravity into the filaments and clusters we now observe. The pattern is one of coherence. The invisible matter does not lie in isolated clouds, but forms an interconnected network stretching through what we once dismissed as void. Such revelations unsettle the notion of emptiness, the apparent darkness. Between galaxies is not absence, but framework, a hidden skeleton holding the universe together. In cultural terms, this resonates with myths of the world tree or cosmic net, the Norse Yggdrasil, the Hindu Indra's net, symbols of an unseen structure that links all things. These ancient metaphors, born in times without telescopes, capture an intuition that reality is bound together by hidden threads. Modern science, equipped with equations and detectors, seems to converge upon a parallel insight, though stripped of mythic ornament. Yet the acknowledgement of this invisible structure raises disturbing questions. If galaxies are shaped by forces we cannot see, what does that imply for our confidence in observation itself? In neuroscience, experiments on perceptual masking show how easily the brain can be influenced by stimuli presented below the threshold of awareness. A fleeting flash or subliminal image, though unseen consciously, alters neural activity and decision-making. In an analogous way, the cosmic web may be acting upon galaxies in ways we can measure only indirectly, influencing their growth, their collisions, and their fate, while the determinant itself remains elusive. Every improvement in mapping techniques seems to deepen the paradox. The more clearly the filaments are traced, the more apparent it becomes that what we call the visible universe, the stars, nebulae, and luminous galaxies, is only a minor fraction of a greater whole. Human senses, evolved to navigate the narrow environment of Earth, are poorly suited to apprehend such scales. Even our instruments, tuned to photons and electromagnetic radiation, capture only the distortions rather than the substance. What lies within those filaments remains concealed, suggested by mathematics, but resistant to direct touch. This resistance provokes a disquiet that extends beyond physics. It forces a confrontation with the limits of cognition itself. The mind, like the telescope, is an instrument shaped by constraints. Just as optical lenses reveal only a slice of the spectrum, the human brain reveals only a slice of reality, reconstructed from incomplete data. If the cosmic web is the true stage of the universe, then our perception of galaxies as primary may be nothing more than a cognitive illusion, a surface rendering of a deeper, hidden order. And that deeper order, still veiled, presses against the edges of our understanding, suggesting that what lies in the darkness between galaxies may hold truths we are not yet prepared to face. The faint tracery of the cosmic web, mapped through distortion and afterglow, conceals within it a subtler substance, an intergalactic medium so diffuse that it defies intuition. This medium is neither the familiar vacuum of laboratory physics nor the dense clouds of gas found within galaxies. It is a realm of tenuous plasma, the thinnest form of matter stretched across unimaginable scales, and yet it accounts for a substantial portion of the universe's visible content. Its presence complicates the picture of emptiness and challenges assumptions about how galaxies form, evolve, and interact. Detecting such a medium required techniques of extraordinary sensitivity. Astronomers turned to X-ray telescopes, instruments capable of perceiving photons emitted at energies far higher than the human eye can register. Observations from missions like Chandra and XMM Newton revealed faint emissions threading the spaces between galaxies. These signals indicated temperatures in the range of millions of degrees Kelvin, an astonishing heat, though spread so thinly that the density was lower than the best vacuums achieved on Earth. The paradox is unsettling, a space both hot and empty, burning without flame, invisible except through instruments designed to capture the most elusive photons. This plasma is believed to exist in multiple phases. Some of it is relatively cool, detectable in ultraviolet absorption lines when light from distant quasars passes through it. Some is hotter, glowing faintly in X-rays. And an even more elusive component may exist at intermediate temperatures, neither cool enough for ultraviolet detection nor hot enough for strong X-ray emission, a hidden reservoir known as the warm-hot intergalactic medium, or WIM. Cosmological simulations predict that a large fraction of the universe's baryons, the ordinary matter made of protons and neutrons, resides in this WIM, sequestered between galaxies like water dispersed in mist. The idea that most of the ordinary matter of the cosmos lies in an invisible form echoes a theme familiar to psychology: the role of latent structures that shape cognition without reaching consciousness. Just as subliminal cues influence decision-making beneath awareness, the intergalactic medium exerts gravitational and thermal effects on galaxies while remaining unseen to the senses. The mind's predisposition is to focus on the discrete, planets, stars, galaxies, while neglecting the continuum that binds them. Yet the continuum may govern the terms of existence, providing the medium in which the visible structures are suspended. The plasma's importance becomes clear when considering how galaxies acquire their gas. Galaxies cannot form stars without a steady supply of hydrogen. Yet the stars themselves consume this fuel over time. The intergalactic medium acts as a reservoir, feeding galaxies through filaments that funnel material inward. High resolution. Simulations of galaxy formation reveal narrow streams of gas flowing along dark matter filaments, cooling as they enter galactic halos and condensing into the raw material of stars. In this sense, the faint plasma of the void is the bloodstream of the cosmos, circulating resources across incomprehensible distances. Detection of this process has come from ingenious techniques. One method involves studying the absorption lines, imprinted on the spectra of quasars, enormously luminous beacons powered by supermassive black holes. As quasar light passes through intervening matter, it acquires absorption features, the fingerprints of hydrogen and heavier elements in the EO medium. These Lyman alpha forests, as they are called, reveal a tangled record of gas distributed across cosmic distances. Another approach, the Sunyaev-Zeldovich effect, measures distortions in the cosmic microwave background caused by hot plasma scattering photons. Each method exposes another layer of the hidden medium, piecing together a picture that remains incomplete yet compelling. The presence of heavy elements in this medium carries unsettling implications. Elements such as oxygen, carbon, and iron are produced in stars and dispersed into space through supernova explosions. Their detection in eyes. The intergalactic medium means that galaxies are not closed systems. They bleed their material into the void. Over billions of years, shock waves from supernovae, galactic winds, and violent mergers have driven enriched gas outwards, seeding the intergalactic environment with the ashes of stellar death. The very atoms that form life on Earth may once have drifted through these tenuous filaments, scattered into the void before being drawn into new galaxies and new stars. Yet the void resists simple interpretation. The whim remains difficult to detect directly, its presence inferred from subtle signals rather than clear imaging. Astronomers estimate that up to half of the baryonic matter predicted by cosmological models may reside in this hidden form, a discrepancy known as the missing baryon problem. The irony is stark. Even the fraction of matter that should be ordinary, made of familiar particles, evades us when dispersed across intergalactic scales. The dark matter and dark energy mysteries remain larger, but the missing baryons remind us that even the known categories of existence dissolve into invisibility when spread thinly enough. The psychological effect of this realization is not trivial. Humans are accustomed to associating matter with solidity, tangibility, and presence. The intergalactic medium inverts this expectation, presenting a case where matter is simultaneously present and absent, real in its cumulative effect, absent in its perceptibility. This duality parallels the way the mind handles ambiguity, as in binocular rivalry experiments where competing images presented to each eye cause perception to alternate, never settling into a single coherent picture. In the same way, the intergalactic medium forces us to hold incompatible notions at once, an environment both void and full, invisible yet substantial. Such paradoxes extend further. The hot plasma not only connects galaxies, but may also influence their fates. By exerting pressure on galactic halos, by stripping gas from smaller galaxies plunging through clusters, by diffusing heat into the structures it permeates, the intergalactic medium shapes the tempo of cosmic evolution. And yet, because it hides in darkness and faint signals, we remain on the threshold of comprehending its full role. Every new observation pushes the boundaries slightly outward, hinting that the void between galaxies is not a passive backdrop, but an active participant, carrying forces and reserves whose consequences reach farther than our present vision can follow. The thin plasma spread across intergalactic space reveals itself reluctantly, but the problem of unseen matter presses further into realms that even plasma cannot explain. The gravitational anomalies traced by galaxies, clusters, and lensing arcs demand a substance beyond ordinary particles, something immune to electromagnetic detection, something that neither absorbs nor emits light. Theories of dark matter emerged from this demand, not from speculation, but from necessity. Without it, the structure of the universe collapses into contradiction. With it, we enter a domain where physics confronts its own limits. Several candidates have been proposed to embody this hidden mass. The most widely considered are WIMPs, weakly interacting massive particles. These hypothetical particles would possess mass sufficient to account for the gravitational effects observed, yet interact so rarely with ordinary matter that they would drift through planets, stars, and human bodies without notice. Entire generations of detectors have been built in deep underground laboratories, shielded from cosmic rays by mountains of rock, waiting for the faintest interaction. Photomultiplier tubes sit immersed in liquid xenon or argon, hoping to catch the flash of a single collision between a WIMP and an atomic nucleus. Yet, decade after decade, the silence persists. Another class of candidates comes in the form of axions, ultralight particles originally proposed to resolve a problem in quantum chromodynamics. Unlike WIMPs, axions would be so light and numerous that their collective presence could behave as a kind of cosmic field. Experiments such as ADMX, using resonant microwave cavities under strong magnetic fields, attempt to convert axions into detectable photons. The search requires instruments of exquisite sensitivity, tuned to listen for a whisper beneath the noise of the cosmos. Despite ingenious designs, the results remain elusive. Sterile neutrinos offer a third possibility. Unlike the three known flavors of neutrinos, which interact weakly and have been detected in solar fluxes, and particle accelerators, sterile neutrinos would interact only through gravity. If they exist, they might have left traces in the early universe, influencing the distribution of galaxies or leaving imprints in the X-ray background. Researchers have scoured data for such signals, occasionally reporting tantalizing anomalies. A faint, unexplained X-ray line at 3.5 He sparked debate about its potential link to sterile neutrinos, but consensus remains unsettled. The persistence of non-detection places cosmology in a peculiar psychological state. The evidence for dark matter's existence is overwhelming in its gravitational effects, yet the inability to capture it directly forces scientists into a condition akin to studying shadows on a wall. Theories multiply, detectors refine, but the object of pursuit remains hidden. This mirrors the way unconscious drives shape human behavior without presenting themselves to awareness. Freud described the unconscious as known only through its distortions, its slips, its resistances. Dark matter, too, is apprehended only through its gravitational distortions upon galaxies and light, refusing direct self-disclosure. The search extends beyond laboratories. Astronomers look for indirect signs, such as annihilation products. Dark matter consists of particles that occasionally collide and annihilate. They might produce gamma rays or neutrinos detectable by satellites and ground-based observatories. The Fermi Gamma Ray Space Telescope has searched the center of the Milky Way for excess gamma-ray emissions, some of which appeared to fit dark matter predictions. Though alternative astrophysical explanations, such as pulsars, compete. Like an optical illusion that shifts when stared at, the signal resists interpretation, reinforcing the ambiguity rather than resolving it. This ambiguity carries a psychological weight. Humans are uncomfortable with persistent absence, with problems that resist closure. Cognitive science has shown that uncertainty activates the brain's anterior cingulate cortex, the region associated with conflict monitoring and error detection. The dark matter enigma becomes not just a physical problem but a cognitive irritant, a wound in the fabric of comprehension that refuses to heal. Our species evolved to resolve patterns quickly, to distinguish predator from shadow. Yet here, the shadow stretches across the cosmos, unyielding to resolution. The cultural echoes of such mystery are not new. Ancient traditions often placed power in what could not be seen. The Egyptian god Amun, whose name means the Hidden One, was worshipped as the invisible force behind visible forms. In Hindu philosophy, Maya referred to the veil obscuring true reality. In both myth and science, hiddenness itself becomes a form of power, a reminder that visibility is not equivalent to significance. Dark matter inhabits this same territory, unseen, untouchable, yet shaping the dance of galaxies across billions of years. Meanwhile, simulations of cosmic evolution reinforce the necessity of this hidden component. Without dark matter, the tiny fluctuations in the early universe, mapped in the cosmic microwave background, could not have grown into galaxies within the available time. Ordinary matter, slowed by radiation pressure, would have formed structures too late. Dark matter, free from such interactions, could collapse earlier, forming gravitational wells into which baryons later fell. In this sense, the visible universe is not primary but parasitic, draping itself over an invisible scaffolding that predated it. And yet, each theoretical advance opens further questions. If dark matter particles exist, why have none appeared in the most sensitive detectors ever built by human ingenuity? If they annihilate, why are their signals so ambiguous? If they do not annihilate, why do they remain so perfectly silent? The silence gnaws at the boundaries of physics itself, forcing some to consider radical alternatives, modifications to gravity, extra dimensions, or entirely new frameworks of interaction. None yet command consensus. The consequence is a landscape where the unknown exerts more influence than the known, where the largest structures of the cosmos are governed by a substance we cannot touch. This inversion destabilizes the human assumption that visibility grants primacy. Just as psychological experiments on inattentional blindness show how subjects can fail to see a figure crossing their field of vision while focusing on a task, cosmology reveals how our fixation on light may blind us to the dominant presence in the universe. The darkness between galaxies ceases to be passive space. It becomes an active riddle, one that presses against the edge of comprehension with silent weight. The mystery of unseen matter alone would be destabilizing, but cosmology confronts an even more disquieting force: the acceleration of the universe itself. When Edwin Hubble first measured the recession of galaxies, the picture that emerged was of a universe expanding from a denser origin. Gravity, it was assumed, would slow this expansion, just as a ball thrown upward decelerates under the pull of Earth. Yet in the late 1990s, two independent teams measuring the brightness of distant Type Ia supernovae discovered the opposite. Instead of slowing, the expansion of space was accelerating, as though some unknown energy were stretching the fabric of the cosmos. This discovery required a profound revision of the cosmic ledger. The force responsible was named dark energy, though the term conceals more than it reveals. Unlike dark matter, which exerts gravitational attraction, dark energy appears to push space apart. Estimates based on supernovae, the cosmic microwave background, and large-scale structure suggest that dark energy constitutes nearly 70% of the total energy density of the universe. It is not an accessory, but the dominant ingredient, dictating the trajectory of cosmic history. One candidate explanation is the cosmological constant, L, which Einstein had once inserted into his equations of general relativity to preserve a static universe. After Hubble's discovery of expansion, Einstein abandoned L, reportedly calling it his greatest blunder. Yet observations suggest that some form of vacuum energy, an intrinsic property of space itself, behaves like a cosmological constant. Quantum field theory predicts that the vacuum seethes with fluctuations, virtual particles appearing and vanishing in accordance with Heisenberg's uncertainty principle. If these fluctuations carry energy, they could generate a repulsive pressure. The problem is magnitude. Naive calculations predict a vacuum energy density more than 10 to 20 times larger than observed, a discrepancy so vast that it has been called the worst prediction in physics. Alternative models posit a dynamic field, dubbed quintessence, that evolves over time rather than remaining constant. Unlike the rigid cosmological constant, quintessence could vary in strength, its energy density changing as the universe expands. The search for signs of such variation continues through measurements of the expansion rate at different epochs, but so far, the evidence remains ambiguous. Other proposals invoke modifications to general relativity itself, suggesting that gravity on cosmic scales behaves differently than within solar systems. Each approach struggles to reconcile theoretical elegance with observational precision, leaving the question unresolved. The psychological impact of this puzzle mirrors the unease of encountering ambiguity in perception. Just as the Necker cube flips between orientations, resisting a stable interpretation, cosmology oscillates between models of vacuum energy, dynamical fields, and altered gravity. Each framework provides a possible orientation, yet none resolves the underlying ambiguity. The human mind, evolved to resolve patterns quickly, finds itself disoriented by a universe that refuses closure. The consequences of dark energy are profound. If its influence continues, galaxies not gravitationally bound to one another will recede faster and faster, drifting beyond the horizon of visibility. The observable universe will shrink in effective terms as distant light becomes red-shifted into oblivion. The cosmic web itself will thin, filaments stretching, clusters dispersing. A universe dominated by dark energy trends not toward collapse, but toward dilution, a slow unraveling where structure fades into isolation. Yet what is most unsettling is the locus of this effect, the very voids between galaxies. Dark energy does not operate within galaxies as a local force. It is a property of space itself, manifesting most dramatically where space is abundant. The emptier the region, the stronger the presence of expansion. In this way, the darkness between galaxies becomes the arena where the universe's fate is written. The same expanses once thought to be inert absence now emerge as active engines of acceleration, pushing the cosmos outward in defiance of gravitational expectation. The resonance with altered states of consciousness is striking. In meditation, or sensory deprivation, it is often not the presence of stimulus, but the absence of it that generates transformation. The mind, unanchored by input, begins to drift, producing hallucinations, distortions of time, or sensations of boundlessness. Just as the void in consciousness generates experience, the cosmic void generates expansion. Absence becomes active. Silence becomes force. Darkness becomes decisive. The parallel is not literal, but metaphorical, underscoring how both the psyche and the cosmos find power in what appears empty. In cultural imagination, forces that push apart carry a sense of unease. Attraction, whether gravitational or emotional, feels comprehensible. It binds and gathers. Repulsion, by contrast, carries associations of alienation and disintegration. Dark energy embodies this latter quality on a cosmic scale. It does not unite. It separates, ensuring that the future of the universe is one of dispersal. This vision unsettles not only physics, but also the human longing for coherence, for a universe drawn together rather than driven apart. The precision of modern surveys continues to sharpen the picture. Baryon acoustic oscillations, the faint imprints of sound waves in the early plasma, serve as a standard ruler for cosmic expansion, allowing astronomers to chart how the rate has changed over time. Weak lensing surveys add further constraints, mapping how structure grows under the competing influences of gravity and dark energy. Each measurement narrows the possibilities, yet the essence of dark energy remains untouched. A force named by absence, defined by what it does rather than what it is. As the data accumulate, the tension grows sharper. If dark energy is a constant, its future is fixed. If it is dynamic, the future may diverge in ways we cannot predict. The possibility of variation opens unsettling horizons. A universe accelerating more rapidly, tearing structures apart more violently. Or a universe where acceleration slows, replaced by contraction. The unknown sits not at the margins, but at the very heart of cosmological fate, embedded in the darkness between galaxies that expands even as we measure it. The expanding void, animated by dark energy, is not empty of more familiar forces. Within those stretches of blackness drift objects so difficult to trace that their very existence was long dismissed as speculative. These are black holes wandering outside the boundaries of galaxies, detached from luminous hosts, invisible except through indirect gravitational clues. Unlike the supermassive black holes anchored at galactic centers, or the stellar mass remnants born in clusters of stars, these rogues inhabit the in-between, traversing intergalactic space with no anchor, exerting influence yet resisting discovery. The origin of such bodies lies in violence. When galaxies collide, their gravitational centers may not perfectly merge. Numerical simulations show that asymmetric ejections of gravitational waves during black hole mergers can impart a recoil, a kick sufficient to hurl the newly merged black hole out of its host. In other cases, three-body interactions among supermassive black holes can eject one from the system entirely. Stellar mass black holes, too, may be ejected through supernova asymmetries or gravitational interactions set adrift into the larger structures of the cosmic web. Once expelled, they carry no luminous signature, no surrounding stars to betray their location. Detecting such entities requires methods as subtle as those used to trace dark matter itself. Gravitational microlensing, where the passage of a compact object bends and magnifies the light of a background star, offers one possibility. Microlensing surveys have occasionally revealed lensing events consistent with compact, non-luminous masses, though separating rogue black holes from other dark objects remains difficult. More recently, gravitational wave detectors such as LIGO and Virgo have provided indirect evidence. The rates and masses of detected mergers suggest populations of black holes that may wander far from their points of origin, awaiting collisions in the darkness between galaxies. The presence of such wanderers shifts the character of the void. It is not merely diffuse plasma and invisible scaffolding. It is punctuated by wells of infinite depth, gravitational traps moving silently through space. Each rogue black hole represents an erasure of matter from visibility, a point where information disappears from the domain of light. To imagine the void populated by such entities is to confront a landscape not of absence, but of lurking thresholds, each capable of swallowing what crosses its horizon without trace. The psychological resonance is immediate. In cognitive science, the notion of blind spots in perception highlights how absence of information is rarely experienced as absence. The visual system fills the optic disc, the point on the retina where no photoreceptors exist, with surrounding patterns concealing the gap. The mind refuses to admit to blindness. In much the same way, the void between galaxies may conceal populations of black holes unacknowledged because our instruments, like our eyes, prefer to complete the picture with continuity rather than acknowledge rupture. Historical accounts reveal how cultures have long imagined the danger of hidden gulfs. In seafaring traditions, the ocean was often described as haunted by unseen whirlpools, capable of swallowing ships without warning. The myth of Charybdis, in Greek legend, embodies this anxiety, a hidden vortex lurking beneath calm waters. Rogue black holes in intergalactic space present an uncanny parallel. Gravitational whirlpools without visible trace, capable of altering trajectories and consuming matter without a flicker of light. Astrophysical modeling suggests that their presence could subtly influence the distribution of galaxies and the heating of the intergalactic medium. A solitary black hole accreting sparse gas produces faint X-ray emissions, detectable only with long exposure and careful filtering. A swarm of such objects drifting through filaments could contribute to background radiation fields or to the mysterious heating of intergalactic plasma beyond what standard models predict. Their effects are cumulative, shaping environments without ever announcing themselves as individuals. The scale of their invisibility is sobering. A supermassive black hole millions of solar masses across could traverse the void for billions of years without being detected directly. Its gravitational influence would distort trajectories only in its immediate neighborhood, leaving little sign for distant observers. The universe could contain countless such wanderers, each contributing silently to the distribution of mass, each invisible to light but real in consequence. This hidden population mirrors the way unacknowledged memories or traumas operate in the psyche. They may not surface in conscious awareness, yet they shape thought, behavior, and emotion through indirect pathways. Just as a rogue black hole alters its environment without being seen, unconscious forces bend the paths of cognition, producing effects without disclosing their origin. The parallel underscores the discomfort of acknowledging that both the cosmos and the mind are structured by presences that elude perception. Speculative theories extend the implications further. If primordial black holes formed in the earliest instance after the Big Bang, they could populate intergalactic space in vast numbers, masquerading as part of the dark matter budget. Some ranges of mass for primordial black holes remain consistent with observational limits, leaving open the possibility that a fraction of the unseen scaffolding of the universe is composed not of exotic particles, but of collapsed matter from the beginning of time. The void would then not merely harbor wanderers expelled from galaxies, but relics of a more ancient epoch, survivors from the first fractions of a second of cosmic history. The consequences of such a scenario are difficult to overstate. It would mean that the invisible engines of gravity between galaxies are not only anonymous but primordial, woven into the universe at its inception, silent witnesses to every stage of cosmic unfolding. Whether or not primordial black holes constitute dark matter, the notion deepens the sense that the void is populated by forces that shape the universe while refusing visibility. And as gravitational wave detectors improve, with new observatories, like LISA planned to probe lower frequency signals across intergalactic distances, the likelihood increases that more of these silent masses will reveal themselves, not through light, but through the ripples they send across space-time. Yet each detection will also raise questions. How many more remain unseen? How deeply the void is seeded with wells of gravity? And how much of cosmic history is written in events we have not yet learned to register? The possibility of hidden black holes drifting through intergalactic space brings with it a further puzzle: the strange signals that reach us after traversing these same vast distances. Among the most enigmatic of these are fast radio bursts, or FRBs, millisecond flashes of radio waves so intense that they outshine entire galaxies during their brief existence. The first was discovered in 2007 in archived data from the park's radio telescope, a burst that lasted less than 5 milliseconds, yet released as much energy as the sun emits in days. Since then, hundreds more have been catalogued, scattered across the sky, with many appearing only once and a few repeating unpredictably. FRBs present a double mystery. Their sources remain uncertain, ranging from magnetars, highly magnetized neutron stars, to more exotic possibilities. But their passage through intergalactic space provides an unexpected tool. As the radio waves travel, they are dispersed, with higher frequency components arriving slightly earlier than lower frequency ones. The degree of dispersion encodes information about the density of electrons in the medium they traverse. In effect, FRBs function as probes, sketching the otherwise invisible matter between galaxies. The faint plasma of the intergalactic medium, impossible to weigh directly, leaves fingerprints on the timing of these signals. This makes FRBs not merely astrophysical curiosities, but instruments of measurement. By analyzing the delay patterns, astronomers can infer how much ionized material the signal has encountered. A landmark discovery in 2020 used a well-localized FRB to confirm the presence of the missing baryons, the ordinary matter that had long evaded detection. The burst's dispersion matched predictions that vast quantities of baryonic material were hidden in intergalactic space, invisible to telescopes but real in their cumulative effect. In this sense, FRBs act as whispers from the void, carrying messages written not by their source alone, but by every particle they pass along the way. The unsettling aspect lies in their unpredictability. They erupt without warning, last for less than the blink of an eye, and vanish, leaving only data imprints on radio receivers. Their randomness mirrors psychological phenomena of fleeting perception, subliminal flashes that alter neural processing without entering awareness. Just as the mind can be influenced by a millisecond stimulus unseen by consciousness, cosmology is influenced by millisecond bursts that reveal truths otherwise inaccessible. These bursts remind us that knowledge is sometimes carried not by the persistent and stable, but by the sudden and transient. Events so brief, they border on the imperceptible. The scale of their brightness also defies easy intuition. For a source, no larger than a neutron star, to generate such colossal bursts suggests mechanisms operating under extreme physical conditions. Magnetars, with fields trillions of times stronger than Earth's, are plausible culprits, releasing pent-up magnetic energy in catastrophic flares. Yet even this explanation leaves questions, particularly for repeating FRBs that show complex, structured signals. Some bursts exhibit periodic activity windows, as if governed by hidden rhythms. Others show frequency drifts, downward sweeps that hint at plasma processes still poorly understood. The variety resists simple categorization, forcing researchers to consider that multiple mechanisms may be at work. The cultural imagination cannot resist overlaying such enigmas with symbolic weight. Brief, bright signals emerging from the darkness of intergalactic space inevitably evoke metaphors of communication. While astrophysics anchors them in natural processes, the psychological pull toward interpreting them as messages is strong. Studies of pattern recognition show how the human brain is predisposed to detect agency in noise, to seek intentional signals where none exist. FRBs exploit this bias, carrying the form of sudden messages even as their content remains astrophysical. The temptation to read them as cosmic beacons reflects not only scientific curiosity, but also cognitive instinct. Beyond the temptation of interpretation lies a more tangible implication. The use of FRBs as probes extends the reach of measurement, deeper into the void. With every new detection, astronomers refine their map of intergalactic matter, constructing a picture of what once seemed unreachable. Yet each refinement also highlights the incompleteness of knowledge. If bursts can reveal baryons, what might they reveal about interactions with dark matter, magnetic fields, or structures still beyond present theory? The signals are not exhausted by current explanations. They open rather than close possibilities. There is also the unresolved question of why some sources repeat, while others remain silent after a single burst. The difference may reflect distinct astrophysical origins, or it may conceal an as-yet unrecognized principle. The intermittent repetition evokes comparisons to rhythms in biology: heartbeats, neuronal firing, circadian cycles. In neuroscience, rhythmic activity organizes perception and action, yet much of it occurs outside awareness, shaping experience from the background. In cosmology, repeating FRBs suggest that hidden rhythms may structure events in the void, rhythms we glimpse only in fragments, never in continuous flow. The reach of these bursts across billions of light-years adds another layer of disquiet. Each FRB we detect began its journey when Earth's continents were arranged differently, when life forms unlike any living today moved across the planet. They carry not just information about intergalactic matter, but a reminder of temporal depth, of signals launched before human consciousness existed, arriving into our brief present. They collapse the distance between the most fleeting of events and the most expansive of timescales, forcing recognition of scales alien to human intuition. As radio arrays grow more powerful, with instruments like CHIME and the forthcoming Square Kilometer Array, detections multiply at a rate once thought impossible. What was once a handful of unexplained events has become a torrent, and with the torrent comes both clarity and confusion. Patterns emerge, yet anomalies proliferate, ensuring that the bursts remain an open question. Each new signal bends our models slightly, hinting at complexities not yet captured. The void speaks more often than we expected, but what it is saying remains uncertain, a conversation we are only beginning to overhear. And so, the darkness between galaxies ceases to be silent. It is threaded not only with plasma and mass, but with sudden eruptions of energy that traverse its depths. These signals, arriving unbidden, compel us to reconsider the void not as absence, but as medium, a stage where unseen processes generate flashes of revelation. Yet every burst leaves in its wake a residue of ambiguity, as if the cosmos were intent on showing enough to provoke inquiry, but not enough to resolve it. In the intervals between bursts, in the silence that stretches across eons, the question of what else the void may conceal presses more urgently against the edges of thought. The fleeting signals that illuminate the dark pathways between galaxies also force a deeper confrontation with time itself. To measure dispersion, redshift, or the faint absorption imprinted upon a beam of light is to recognize that the universe is not static, but in motion, evolving along trajectories dictated by hidden forces. When cosmologists project these trajectories forward, they encounter visions of the cosmos that are as disturbing as they are mathematically consistent. The fate of all structure appears bound to the same void that now carries bursts and distortions to our detectors. One scenario, derived from the dominance of dark energy, is the slow progression toward heat death. In this vision, galaxies not gravitationally tethered will drift apart, their light stretched beyond detectability as expansion accelerates. Over trillions of years, stars will exhaust their fuel, leaving behind white dwarfs, neutron stars, and black holes. Even these remnants will decay, their particles slowly radiating away through quantum processes such as Hawking radiation. The void between galaxies will no longer be punctuated by luminous clusters, but will become an ocean of near-uniform darkness, filled with low-energy photons and subatomic particles diffused into equilibrium. Yet heat death is not the only trajectory considered. If dark energy evolves with time, if its strength increases rather than remains constant, the acceleration could intensify into what some theorists call the Big Rip. In this model, expansion would grow so violent that it would eventually overwhelm not only galactic bonds, but also stellar systems, planets, and even atomic structures. The void would not simply stretch galaxies away from one another, but would tear apart the very fabric of matter, leaving no coherent forms behind. The unsettling aspect of this scenario lies not only in its destructiveness, but in the idea that the void itself becomes an agent of disassembly, undoing what gravity and fusion once built. Other possibilities rest upon the unknown nature of dark matter and its interplay with cosmic expansion. If dark matter proves unstable, decaying into lighter particles over immense timescales, its gradual disappearance could alter the balance of cosmic structure. Clusters would dissolve more easily, filaments would thin, and the scaffolding of the universe would weaken. The darkness between galaxies would then become the archive of decay, carrying within it the relic radiation of disintegrated mass. Such a future would not arrive in abrupt cataclysm, but in a slow erosion, a gradual yielding of order to invisibility. Psychological parallels emerge in the way humans process awareness of mortality. Just as individuals confront the eventual dissolution of the body, cosmology confronts the eventual dissolution of form on a universal scale. In both cases, the mind struggles against comprehension of timescales and processes beyond direct experience. Studies in existential psychology suggest that awareness of mortality provokes both anxiety and meaning-making, driving cultures to generate myths of continuity. Cosmological projections play a similar role. They are not merely calculations, but attempts to situate meaning against the overwhelming presence of void and decay. Yet even within these models, uncertainty persists. Observations of the Hubble constant, the current rate of cosmic expansion, have produced discrepancies depending on the method of measurement. Data from the early universe, such as the Planck satellite's mapping of the cosmic microwave background, suggest one rate, while measurements of supernovae and Cepheid variables in the nearby universe suggest another. The tension between these results, known as the Hubble tension, implies that something fundamental about cosmic expansion may be missing from present theory. This discrepancy extends into projections of the future, reminding us that the fate of the cosmos is not a settled narrative, but an unresolved calculation. The role of the void in these possibilities is not peripheral, but central. Expansion occurs, not within galaxies, but between them, in the spaces where gravity loses its grip. As those spaces grow, they dictate the trajectory of cosmic destiny. The void is not simply where events fail to occur, it is where the future is decided. This inversion, where absence becomes determinant, mirrors cognitive research on inhibition. In neural circuits, inhibitory signals do not merely silence activity, but sculpt patterns of thought, shaping what emerges into consciousness. The void plays a similar role on a cosmic scale, sculpting what survives and what dissolves through the pressure of expansion. Speculation extends further into the long tail of time. After galaxies fade, after black holes evaporate, the universe may approach a state where only the faint hum of radiation persists. Yet even then, quantum fluctuations could generate brief sparks of structure, virtual particles appearing momentarily before disappearing again. Some theorists have speculated that, given infinite time, fluctuations might produce entire new regions of order, perhaps even self-contained pocket universes. In such a vision, The void does not simply end in silence, but continues as a field of restless potential, never static, always capable of fleeting emergence. The paradox of such projections is that they rest upon present ignorance as much as present knowledge. We do not yet know the true nature of dark energy, whether it is constant or dynamic. We do not know if dark matter is stable or decays across unimaginable timescales. We do not know whether the apparent constants of physics are fixed or whether they shift subtly over eons. Every projection into the future is therefore conditional, dependent upon variables that remain concealed in the present. The void is not simply the stage for cosmic endings. It is the reservoir of unknowns that prevent us from stating which ending will unfold. In this sense, the fate of the universe is written in absences, forces we cannot see, structures we cannot touch, and signals that arrive only as distortions. The galaxies shining now, the stars burning brightly in our night sky, may be brief exceptions against a backdrop of darkness that stretches across time as well as space. And as instruments extend their reach, detecting fainter bursts and subtler distortions, they remind us that each answer pushes against a deeper stratum of uncertainty, one that waits in the silent expanses between galaxies, holding consequences we have not yet begun to grasp. If the darkness between galaxies decides the trajectory of cosmic history, then the scale of ignorance we face is more profound than any single unanswered question. Measurements across decades suggest that nearly 95% of the universe is composed of entities we cannot directly detect: dark matter and dark energy. The luminous portion, all the stars, planets, nebulae, and galaxies visible to telescopes, is only a trace amount, a surface froth upon a sea of hidden constituents. This imbalance reshapes the definition of what is real. It implies that human perception, and even the instruments we build to extend perception, operate within a narrow aperture that registers only the exception rather than the rule. This recognition destabilizes the anthropocentric instinct to equate visibility with significance. In psychology, attentional blindness experiments show that subjects can miss obvious stimuli when their focus is narrowly constrained, such as failing to notice a figure crossing a scene while counting objects. The cosmos presents a similar challenge. We may be attending to the dazzling lights of stars while overlooking the far greater substance structuring their existence. The tension lies in acknowledging that our position as observers is shaped by biases of detection, and that what appears to us as the universe may be no more than a filtered shadow of a deeper reality. The boundary of what remains unseen is not static. Each refinement of observation shifts the margin slightly, uncovering new traces of structure. Yet the magnitude of what remains hidden suggests that no incremental improvement will suffice to resolve the whole. In neuroscience, the majority of brain processing occurs outside awareness, with consciousness representing only a narrow selection of neural activity. The cosmos appears to operate by a similar principle. The visible fraction is but a sliver of the whole, a privileged but misleading cross-section of an immense hidden system. The unease this provokes is amplified by the historical tendency to misinterpret absence. Cultures across time have projected meaning into what could not be seen, from spirits inhabiting empty forests to gods inhabiting the sky. In each case, the unseen was imagined as potent, its very invisibility granting it authority. Dark matter and dark energy now occupy a similar place in scientific cosmology. Forces known only through their influence, yet indispensable to every model. They become modern heirs to the archetype of the hidden, not as superstition, but as empirical necessity. Their power lies precisely in the refusal to reveal themselves. Speculative physics extends the reach of this hiddenness. Some theories propose that what we call dark matter may consist not of exotic particles within our universe, but of gravitational leakage from other dimensions. String theory, with its requirement of additional spatial dimensions, provides one mathematical framework where such leakage could occur. In this view, the void between galaxies might not only contain invisible matter, but could be a membrane where multiple realities overlap, their gravitational fields intersecting. The suggestion unsettles because it reframes the void not as emptiness, but as interface, a boundary with properties we scarcely comprehend. Quantum cosmology adds another layer. The vacuum is not inert, but a restless field, fluctuating with virtual particles that blink into and out of existence. These fluctuations, undetectable in isolation, may accumulate effects on cosmic scales, shaping the energy density of space. The idea that the void seethes with hidden activity echoes traditions that imagined emptiness as generative, a fertile nothingness out of which forms emerge. The convergence of myth and physics here is accidental, yet it underscores how deeply unsettling it is to imagine that what appears silent may in fact be the source of all dynamics. What remains unresolved is whether these hidden forces are comprehensible within current frameworks or whether they demand an altogether different order of explanation. Cognitive psychology notes that when humans encounter anomalies that cannot be reconciled with existing schemas, they often resort to creating new categories or embracing contradictions. The persistence of dark matter and dark energy may signal that physics stands at such a threshold. Theories multiply not because they are fanciful, but because the existing schema resists accommodation of the data. The mind mirrors this condition. Confronted with irreconcilable input, it oscillates between interpretations, none entirely stable. The cultural implications of this hidden universe are not trivial. If most of reality is invisible, the stories we tell about existence must shift. Human history has often revolved around visible markers, territories, monuments, artifacts. But cosmology reveals that true power lies in what eludes sight. The void between galaxies is not passive backdrop, but dominant actor, and its hidden content determines the arc of cosmic evolution. This inversion, where the unseen outweighs the seen, reverberates across disciplines, forcing reconsideration of what knowledge itself can encompass. And yet, the unanswered remains not just a scientific challenge, but a psychological pressure. To live in a universe where 95% of substance is hidden is to inhabit uncertainty on a scale that dwarfs ordinary experience. The instruments may refine, the models may sharpen, but the proportion of ignorance remains vast. Each discovery seems less a resolution than an unveiling of deeper absences, as though the void retreats as we advance, withholding closure. The sensation is not of approaching completion, but of being drawn deeper into an architecture designed to conceal as much as it reveals. What lies in that retreat is not silence, but a weight of unanswered presence, a reminder that the universe we inhabit is not the universe we perceive. And the more clearly this becomes apparent, the more urgent the question grows: whether human cognition, evolved on a single planet, can ever fully apprehend the hidden forces that stretch across the darkness between galaxies.